Welcome to the Kinematics of Rigid Body Motion. Today we are going to discuss Euler's theorem on the motion of a rigid body. The techniques required to describe the motion of a rigid body have been fully developed. At any instant, the orientation of a body under rigid constraints can be represented through an orthogonal transformation, its elements specified by a suitable set of parameters. As the orientation changes in time, so do the matrix elements become functions of time such that the transformation is time-dependent. If at the initial moment the body axes are coincident with the space axes, then the transformation at the initial moment in time is equal with the identity transformation. But at a different time, the transformation matrix will be different from identity. And nonetheless, the transformation matrix as a function of time is a continuous function, and as such the transformation will evolve continuously from identity. Thus, in the original statement of Euler's theorem for the motion of a rigid body, it is said that the general displacement of a rigid body with one point fixed is a rotation about some axis. What the statement implies is that for such a rotation, one can always find an axis for the fixed point, which is fixed at the polar angles phi and theta, such that when rotating about it with the angle psi, the result of the general rotation is duplicated. Thus, three parameters, the angles, characterize the general rotation, which can also be generated through three Euler angles. If the fixed point is the origin of the body set of axes, the only change incurred in the set is that of its orientation. Therefore, the body set of axes at any time t can be found through a single rotation of the initial set, assumed coincident with the space set. Then, the operation implied in the matrix A describing the physical motion of the rigid body is that of a rotation. Therefore, any vector lying along the axis of rotation will have the same components both in the initial and final set of axes. Since the transformation is orthogonal, the magnitudes of all vectors are automatically preserved. In other words, the theorem is proven if there exists a vector having the same components in both frames. So if that vector is R prime and it is equal with the application of the transformation matrix A on the original vector R, the result of that operation is once again R. This is a special case of a more general problem where when applying the transformation matrix A to the vector R, we obtain the same vector scaled by some quantity lambda. The numbers lambda are generally complex and are known as the eigenvalues of the matrix A. The equation here states the eigenvalues problem in the form of the eigenvalues equation, and its solutions are the eigenvectors of the matrix A. In this language, we can recast Euler's theorem as follows. The real orthogonal matrix specifying the physical motion of a rigid body with a fixed point always has the eigenvalue plus 1. Equation 449 can be recast immediately in the form here, and then we can expand this into the set written here. So, in effect, we have obtained three simultaneous homogeneous equations for the components of the vector R. As such, they cannot furnish definite values of the three components, but only ratios of the set components. Physically, this corresponds to the constraint that only the line direction of the eigenvector can be fixed, and not its magnitude. In effect, this is saying that the product of a constant with an eigenvector is still an eigenvector. Being homogeneous, the system can have a non-trivial solution only when the determinant of the coefficients vanishes, leading to the characteristic or secular equation. So the requirement that this determinant is 0 is or vanishes is equivalent with the expanded form here. And using this formulation of the problem, we can recast Euler's theorem for the motion of a rigid body as follows. For real or orthogonal transformations, the secular equation always has a root, lambda equals with 1. In general, the secular equation will have 3 eigenvalues and 3 eigenvectors x index j of components xij. Thus, a member of the system, this is 451, so it corresponds to the system here, and a member of the system can be written in this form. And then, since we can associate through the representation here, we can associate the eigenvalues of the matrix A with an eigenvalue matrix lambda, which is diagonal. We can reformulate equation 453 as the matrix equation here, which can be multiplied by the inverse of the matrix X of the eigenvectors from the left to obtain this form. So one alternative approach to the eigenvalue problem is that of diagonalizing A through a similarity transformation. Each column of the matrix X contains the components of an eigenvector, and the elements of the diagonal form of A are the eigenvalues. Starting from this identity, which is obvious, we can take its determinant, and the determinant here corresponding to this matrix follows from the fact that the matrix is orthogonal, so the inverse of the matrix is equal to the transpose, and the determinant is of course invariant to a transposition. So we have the form here, and now since A is a proper orthogonal transformation, this determinant in particular is 1, so we obtain the equality here. Now we know that the determinant of a given matrix B multiplied by -1 is equal with -1 to the power of n, where n is the dimension of the square matrix, assuming that B is a square matrix. So we have already proven this, and then it follows that in the case in which n is equal with 3, from the previous result we immediately obtain the formula here. So the secular equation implies immediately that lambda has to be equal with 1. The number of dimensions of space is critical for Euler's theorem. The result is not true in an even number of dimensions. In 2 dimensions, no vector in the space can remain invariant to a rotation, as the axis of rotation is perpendicular to the space in question. Assume now that we fix the value of the third eigenvalue to be equal with 1. Since the determinant of a matrix is invariant to a similarity transformation, if we use the results 454, 455, and the fact that A is a proper orthogonal transformation, then it follows that the determinant is equal with the product of the 3 eigenvalues, which in effect is just the product of the first and second eigenvalues, and this has to be equal with 1. Given the reality of the matrix A, if lambda is an eigenvalue, then so must be the case for its complex conjugate. In the case of complex eigenvalues, usually the components of the associated eigenvectors are also complex, and in that case, for a vector having complex components, we define the square of its magnitude as the dot product between the vector and its complex conjugate, or in matrix form, the matrix product of the row matrix of the vector multiplied with the complex conjugate of the column matrix of the vector. And of course that in the case of an orthogonal transformation, this dot product, this scalar product, if you wish, written either in vector or matrix form, has to be the same before and after transformation, which is in effect what is written here, because the length of the vector is preserved. So using this together with equation 449, which was the statement of the eigenvalue problem, we immediately obtain the result here, which in light of the orthogonal nature of the transformation implies that the product between lambda and its complex conjugate has to be equal with 1. Therefore, if all eigenvalues are real, we have two possibilities. Either all values are equal with 1, which leads to the transformation matrix being the identity matrix, which is just the trivial case, or one of the eigenvalues is equal with 1 and the other two are equal with -1, case which corresponds to a rotation of pi about the axis, which is equivalent to a reflection in the plane normal to the rotation axis. If the eigenvalues are allowed to be complex, then we have, for example, the case where lambda 3 is equal with 1, and then lambda 1 is a complex phase and lambda 2 is its complex conjugate. And this allows for yet another reformulation of Euler's theorem for the motion of a rigid body, the statement now being that any non-trivial real orthogonal matrix has one and only one eigenvalue equal with 1. For an eigenvalue equal with 1, the system 451 can be solved for the components x, y, z and the direction cosines of the axis of rotation. This is not always possible if not all eigenvalues are distinct, but this case is safe from such complications given Euler's theorem. By a similarity transformation, we can always align the axis of rotation with the z-axis, leading to a matrix of rotation of the form here. So we can identify the angle in this complex phase exactly with the angle of rotation about the polar axis, if you will. Furthermore, as the trace of a matrix is invariant to a similarity transformation, we have the trace of the transformed matrix being the result here has to be equal with the trace of the initial matrix, which is just the sum of the diagonal elements or the sum of the three eigenvalues. And in the general case, it is equal with the sum here, which is equivalent with this result. And we see that if for all three eigenvalues, all of them are equal with 1, then the angle of rotation is 0, which corresponds to the trivial case, while if two of the eigenvalues are equal with -1, the angle of rotation has to be equal with pi. Some ambiguities remain, however. If r is an eigenvector, so is -r. Also, minus phi satisfies the equation here as well as the angle phi. From 452, it follows that the transpose of A has the same eigenvalues and eigenvectors. These ambiguities can be addressed to an extent by assigning the negative rotation angle to the transpose of A and fixing the sense of rotation through the right-handed rule. Lastly, at this point, as a corollary to Euler's theorem is the more general statement of the theorem due to Chalet, which says that the most general displacement of a rigid body is a translation plus a rotation. And the above result follows immediately from the introduction of the translation degrees of freedom for the origin point of the body system set of axes. This theorem has a strong form, which states that the body axes are chosen such as to allow for screw motion, namely for the translation to be along the axis of rotation. And this finds use in systems with a screw axis of symmetry, as found, for example, in crystallography study of some specific crystal geometries. As an application, we can consider the following example. Assume that A is an antisymmetric matrix of three dimensions, and then the eigenvalue problem will expand as shown here. And then the condition for a non-trivial solution of the corresponding system of equations is that the determinant of the matrix of coefficients vanishes, and then the vanishing of the determinant will imply the following possible eigenvalues. Either lambda is 0 or lambda is an imaginary number having the imaginary part given by the square root of the sum of squares of the non-vanishing distinct elements of matrix A. And with this in mind, it then follows that the matrix here, which is just the identity matrix plus the matrix of the eigenvalues, immediately will have a non-vanishing determinant. In these conditions, if we define the matrix B to be of the form here, we can write the formula leading to the identity matrix for the matrix here. So we can multiply this with its inverse to obtain the identity matrix. And then what we can do is we can take the transpose of this formula and solve for the transpose of the inverse of the matrix here to obtain this identity. And what this proves straight away then is that the matrix B, defined as here under the conditions stipulated here, is orthogonal. Consider now that the matrix A corresponds to a rotation through an angle pi about some arbitrary axis, and define the matrices B plus minus as the scalar 1 over 2 multiplying the identity matrix plus minus the matrix A. As applying A twice leads to the identity matrix, it follows immediately that the square of either of these matrices, so the square of B plus or B minus, is equals simply to B plus or minus respectively. Now, for the sake of illustration, we can choose the axis of rotation to correspond to the z-axis, case in which the matrix A has the form here, and the expressions for P plus minus also follow as given here. Then, if for some arbitrary vector f having three components, if we apply P plus and P minus to it, we obtain the following. The application of P plus on the vector returns a vector with the single non-vanishing component being fz. So what we obtain is the component of the vector which is parallel to the axis of rotation, and respectively, if we apply P minus to f, we obtain a vector having as non-vanishing components only the components in the plane perpendicular to the axis of rotation. So as any vector with respect to some axis can be decomposed in a perpendicular and parallel component, these components follow simply from the application of the P minus and P plus matrices to the vector, and therefore we can call these projection matrices. Now, if the matrix A happens to reflect R in a plane having the normal n of some orientation given by the components here. So what I mean by reflection now is I am reflecting the vector along the normal to the plane, then the vector obtained through the reflection operation will have the same perpendicular component as to the axis as the original vector, but the parallel component will have the sign changed because the vector is reflected along the axis. And then as the parallel and perpendicular components are given simply by the expressions here, we immediately obtain the general reflection formula as stated in this expression. And we can see that this corresponds to a matrix having the elements shown here. And then you can see immediately that this matrix is indeed orthogonal. However, it is not proper, but rather it is an improper matrix, an improper orthogonal matrix having the determinant -1. And we can use these ideas to prove a very general and remarkable result. Namely, let's assume for the simplicity of the argument that the normal along which we are reflecting is oriented in the y direction. Then we simply apply the reflection matrix to an arbitrary vector to obtain the vector components here. And now let us write this vector in a basis that is rotated with an angle phi over 2 with respect to the original basis. So a basis that is rotated with an angle phi over 2 about the z-axis. What this corresponds to is applying the transpose of the matrix defined in 443 on the vector R1, which returns the results here, which are the components of what we call R2. Now, this rotation has defined a new y-axis, which we will consider to be our new normal, having the components here with respect to the original basis, and we can reflect the vector R2 once again along this direction to obtain the vector R3 having these components. However, if we were to express the vector R3 in the original coordinate system, this corresponds to applying the direct transformation of equation 433 to R3, so the matrix D corresponding to a rotation of phi over 2, and this results in the vector R prime having the components here. But this is simply the vector that will be obtained if from the very beginning we simply rotated the original vector R about the z-axis by an angle phi, with once again with the matrix D defined by equation 433. So what we see here is that a rotation of angle phi is composed from two reflections in planes passing through the axis of rotation and having the planar angle phi over 2. In summary, we have stated Euler's theorem for the motion of rigid bodies, expressing it as a secular equation and as an eigenvalue problem. We have shown that for real, non-trivial orthogonal transformations in three dimensions, there is only one eigenvalue equal with 1, which allows for the determination of the direction cosines of the axis of rotation as well as the angle of rotation. We have studied the simple eigenvalue problem as well as the general formula for reflections and the relation between reflections and rotations. In the following, we will discuss finite rotations. That being said, I want to thank you very much for watching. I hope you found the video worth your time, and I will catch you later. Goodbye.